All right, now that we know quite a lot of our energy terms and what's going on in energy systems, we're going to talk about two types of systems. We're going to talk about closed systems and then open systems. So closed systems are going to be the easier of the two, so that's where we're going to start. So basically the way that we determine if a system is open or closed is whether or not mass is crossing the system boundary during whatever time period is covered by the energy balance that we are undergoing basically in the system. So if mass is crossing the system, right, that is going to be an open system. It's a continuous system. If mass crosses the system, if it doesn't cross the system, if it moves into the system in a batch and something happens and then it comes out, that is a closed system. So our closed system balances are going to be our batch systems, and our open system balances are going to be semi-batch and continuous systems. If we're taking a look at a closed energy balance, generation is going to equal consumption, and they're both going to equal 0. So therefore, we start in a closed system with accumulation equals input minus output. No mass is going to cross this system boundary, but energy can be transferred across the boundary in two different forms, and those forms are heat and work. So what we're going to want to do is we're going to want to write that general balance equation of accumulation equals input minus output in terms of energy. So that's what we're going to start to learn in this upcoming lecture. So let's take that equation, accumulation equals input minus output, and let's rewrite it in terms of energy. So the net energy transferred into a system in minus out is going to equal the final energy of the system minus the initial energy of the system. So that net transfer of in to out represents the accumulation term. There's going to be some final energy of the system and some initial energy in the system as well. So if we add on to this in our system, what we're going to find is that our closed system balance is going to have the form that's on your screen. So Q in this class is going to represent heat. W is going to represent work. So the accumulation, which is the net energy transferred across the system boundaries, is a combination of heat and work in the system. So that's the accumulation terms. Then we will have some initial form of internal energy represented by U, some form of initial kinetic energy, and some form of initial potential energy, which are represented over here, right? Some initial amount. And then we're going to have some final amount of that energy. And so what we can do is we can write our closed system energy balance as Q plus W equals the change in internal energy plus the change in kinetic energy plus the change in potential energy. So this is going to be our closed system energy balance. It always starts from accumulation equals input minus output and has this form. From here, we can cancel these terms if they don't apply to the system, but we need to check and see if they do apply. So this is going to be an important equation that you're going to want to circle and star for your final exam. So that form that you saw on that last slide is the basic form of the first law of thermodynamics for closed systems. So you're going to take thermodynamics. You might be taking it now, we might have taken it, or you might be taking it, but it is the first law of thermodynamics. And if we apply the first law for closed systems, the internal energy is mostly dependent upon chemical composition and temperature and the aggregate state of the system, whether it's solid, liquid, or gas. So we can figure out what's going on with the internal energy by looking at chemical composition and these other components. If a system is not accelerating, if there's not acceleration of some component of that system, the kinetic energy, the change in kinetic energy is going to be 0. So one thing that we're going to want to look for in our problem statements is whether or not the system is accelerating. If it is, we cannot cancel the kinetic energy term, but if it isn't, we can. If the system is not rising or falling with reference to whatever that reference point is, normally the surface of the Earth, then we can cancel potential energy. Remember, we're mostly talking about gravitational potential energy in this class. So if it's not rising or falling with reference to some kind of a surface, we can cancel potential energy. If the systems and its surroundings are at the same temperature, Or if the system is perfectly insulated, this type of process is called an adiabatic process, and that means the change in heat is equal to 0. So what you're starting to see here on this slide is a list of rules for how we can simplify the balances on closed systems. And then the last rule that we're going to have is that if there's no moving parts, electrical currents, or radiation that moves across the system boundary, then the work done on the system, or the work from the system to the surroundings, is equal to 0. So this slide right here gives you an idea of how to take that general balance form of the closed system balance and start to cancel some of those terms as we start to look at our problems. And then lastly, I just want to mention open systems in this lecture. We will see open systems in detail in the upcoming lectures. But an open system process, by definition, mass will cross the system boundaries. So we're always going to have work terms in those types of energy balances. So take that as a note for what's coming up in this particular class, that we are going to start with closed systems. We'll talk about them for a little while, but open systems are going to be more realistic because they are the continuous systems that we deal with. So just keep that in mind as we start to move forward.